Good morning, everyone. Yes, thank you. Good morning, ladies and gentlemen. At the risk of self-plagiarizing, let me welcome you, all of you, the great many of you, warmly to this conference. It is indeed heartwarming to see so many of you. About 1,800, approximately the same number as last year. A wave, a sea of physicists and their friends who flood the Koningshof every year. This is the FOM playground. This is where you meet your friends, but even more so, where you can meet the new kids on the block. What brings you here? You're all very busy. You're either engaged in a struggle with Mother Nature, or trying to get that proposal out or that paper out, or writing proposals against a tight deadline, and probably all of that at the same time. And physicists are not exactly known for their herding instincts. So there must be a rationale that brings you here. You voted with your feet, 3,600 of those. What's so important, so attractive, so much fun about this conference that makes you take 2 full days out of your full calendar? Well, I won't answer that question. Let the coming 2 days show what cannot be put into words. The buzz of a vibrant community. I said you were probably writing proposals against a tight deadline, probably. And life is becoming more and more complex on that front. The number of sources where an individual researcher can apply and find budget for research has increased tremendously in the past years. FOM used to be one of those steady sources of income for you. But under the influence of the new structure of funding of science in the Netherlands, now FOM itself has become part of a network. We co-finance with other parties, with private parties, with ministries, with other fields, with universities. So life has become more complex. Is that a bad thing? We probably fund more physics research than ever before, and excellent research at that. And yes, all those interactions do bring new inspiration, new expertise, do connect us with new people, with new knowledge, and it's at our benefit. But at the same time, the budget that we can offer for you, for our community, that budget as you know it, the instruments as you know them, those have less budget, and we have to live with that. This is a complex world, and it's important that FOM, that we as a community do not lose ourselves in financial regulations, in policy instruments, in governance structures, but keep asking the question, what is it that we really want to do? What will bring our science further? What are our strengths? Where do we see the most exciting physics, the best opportunities for progress? And yes, how can we contribute to solving those grand challenges? And how can we contribute to increasing competitiveness? And with whom? But always starting with the science. So this conference is entirely science-centered. It's about science, it's about our science, it's about your science, it's about who we are, what makes us tick, what drives us, what tickles our imagination. Here we can sample fields that we do not know so well. Here we can link with people in other fields. Here academics can meet with companies and brainstorm about new ideas. So I'd like you to think of this conference as a place of inspiration rather than work. A busy 2 days, your heads will probably spin tomorrow afternoon, but then hopefully on Thursday or in the weekend, you have a quiet moment and you have your Zen experience when you know what it is you really want to do. Because that is, in the end, the question that we as a community will have to answer collectively. What is it we really want to do? We interact in all directions, with private parties, with politics, with other disciplines, but we can only do that effectively if we know what we want to do. And there are a myriad of funding schemes, but we have to put the science first. In picking the best science, that is where nobody can better us. That is our field. We have to put the science first and center, or we have no right to speak. This conference is science-centered. It's broad, it offers very much, and I want to ask you to do just one thing. Don't be polite, don't sit in on the talks of your next door neighbor at home, or your colleague. You know them, you know their work already, and you occupy a seat for others who do want to go to those talks. So, follow my request, go to anything but your own specialization, mingle, sample, get to know new people, sparkle. This convention is the FOM playground. So, if this be FOM's playground, then play on, play on. But just for a minute, please stay put, because we start with a great plenary lecture by Ursula Keller, and Wim Ubachs will introduce her. Wim, can I ask you to the floor?
Yes, my great pleasure and honor to introduce to you the first plenary speaker of today, which is Professor Ursula Keller of the Eidgenössische Technische Hochschule in Zurich, the ETH, as you know it. She leads there a research group, a large research group in ultra-fast physics, and also she leads a Swiss multi-institute program on ultra-fast science. Professor Keller started at the ETH, but then she left after receiving her diploma, as they call it in Switzerland. She did a PhD in Stanford University in applied physics, and then she moved on for several years to Bell Labs, when that still was a flourishing laboratory. She was also a visiting professor at the UC Berkeley, and then also at the Lund Institute of Technology. And apart from doing basic science, she also is a co-founder of two companies, one of which is the optics laser-based company Time Bandwidth Products. Her research interests lie in exploring the frontiers that you can do with lasers, ultra-fast science and technology, and everything you can do with that. Not only the ultra-short pulse generation, frequency combs, then you move on harmonic generation, extreme ultraviolet light, X-rays, and what you can do there. And in particular, she is one of the pioneers of attoseconds. And that's what she will speak about today, about the production of attoseconds and how to do experiments with that. And she goes back to a very old experiment, which is actually the experiments of photoelectron spectroscopy that Einstein clarified to us. But there's always new things to find in photoelectron spectroscopy on how an electron moves away from an atom after being excited. And that will be the topic of our talk, and we all look very much forward to it. Professor Keller, I invite you to give your lecture.
Good morning, everybody. I mean, first of all, I would like to thank the organizers to invite me to this, and I'm just simply overwhelmed. You know, I thought I'm going to kind of a sleepy annual meeting of a national physics conference, and here I am. There's so many physicists I haven't seen on one spot ever, and I think we need to do something similar in Switzerland. I mean, this is amazing. I mean, it's an honor to be here. So, luckily I didn't know I'm gonna give a talk in front of so many people. So anyway, otherwise I wouldn't have slept. So, the talk is about the Attoclock, and with the Attoclock we can actually explore very fundamental processes in quantum mechanics. Actually, the questions you normally ask as a student when you learn quantum mechanics, which you then learn to not ask anymore. And now, in the attosecond spectroscopy, we can go back and actually ask exactly those questions. And I can tell you, everybody has an opinion, and they are different. And it is an exciting field as an experimentalist, because the theoreticians are huffing and puffing after us with our measurements. So of course a measurement is never done alone, and let me just first introduce my co-workers. I mean, when we invented the technique, the Attoclock technique, I actually we tried to explain and understand an experiment that didn't work. And so I couldn't even give it to a postdoc because it was in such a bad shape. I came back from my sabbatical, took over the graduate student, and I worked directly with the graduate student, Patricia Eckel, to try to figure out what the heck is going on. And after we figured it out, we actually realized, wow, this is beautiful, this can do more. I added more people, and so the group grew with a postdoc, then with another graduate student, more postdocs. And I also benefited from a very good collaboration from my colleagues, Reinhard Dörner, who actually taught us how to build up a cold trims apparatus. Then I had a collaboration with Hans Müller from Amsterdam to do the time-dependent Schrödinger equation, which then, because he stopped, unfortunately, and then was taken over by Lars. The work continued. We improved our measurements because initially we could not resolve it, and I expanded the team even further, added more instrumental techniques, the VMIS, and also the theory to explain finally our results that we measured. So, let me give you a little bit of an introduction about short pulse generation. As you know, the first time sub-picosecond pulses were generated in the 70s with the dye lasers. And you know, all the pioneering work has been done with dye lasers, where all the techniques have been demonstrated, pump probe, and so on. And the shortest pulses in the 80s of 6 femtosecond have been produced by Chuck Schenk at Bell Labs. That's why that was also my dream place to go and work. The breakthrough came with a Thai sapphire laser, and within a very short time we produced much shorter pulses than before with more average power, and we pushed the limit so far down that we only had 1 to 2 optical cycles underneath the pulse envelope, which means that we had basically, when you have a near-infrared pulse at 800 nanometer, the optical cycle is only 2.7 femtoseconds. So if you want to move into the attosecond, you obviously had to increase the center frequency. And this was actually done with the so-called high harmonic generation. And high harmonic generation, again, was an experimental discovery, and an explanation came later. So people had more and more powerful lasers, and when you have this laser, you shoot into something and see what happens. And so what happened if you shoot into gases with a very high intensity in the range of 10 to the 13 to 10 to the 15 watt per square centimeter, you actually produce harmonics. So we all know from nonlinear optics that if you increase your intensity, you produce second harmonics, third harmonics, and so on. But what was special about these high harmonics is that you had this plateau. So instead of Taylor expansion, perturbation theory, that your efficiency went down as you go up in harmonics, you actually reached a plateau. And this plateau was the first time really nicely shown by Anne Lullier. And, you know, people were wondering, why do we have this plateau? We can have this plateau going from 1 EV photon energy to 100 EV. So the overall efficiency is 10 to minus 6, but you start with a lot, so you still have enough. You still have nanojoule pulses, you know. So how does it work? And it took a while. So the first discovery of this plateau by Anne Lullier was basically 1988, and it took a while to understand it. And basically today we have in the lab, ultra-fast pulses going from the UV, visible, IR, mid-IR, terahertz, and we can go into these high harmonics, which of course are then in the higher frequency regime, which is absorbed in air, and therefore you need to actually reduce your lab space into vacuum chambers, which is shown here as an example, the Atto line. Now, through the whole process of generating these short pulses, actually, we came up with a different technique, which actually gives right now the highest time resolution that any measurement has been done in the time domain, but it actually doesn't even use attosecond pulses. And this is the Attoclock. So with the Attoclock, we were able to address the question, how long does it take to pull an electron out of an atom? So we normally distinguish between the different regime. So if you are in a photon energy which is much lower the ionization potential, you can either have multi-photon absorption or then this tunnel ionization if the intensity is strong enough, which so that basically the Coulomb potential of your atom gets bent through the laser field so strongly that the electron can tunnel out. But if your photon energy is higher than the ionization potential, then of course you can have a direct emission of a single, through the absorption of a single photon and have the emission. So how long does these processes take? There were a number of measurements. So we basically at ETH used the Attoclock to resolve the tunnel ionization, and it took quite some, I mean, it was a measurable delay, and I will show you afterwards how we measured it. And then other people, for example, measured the photo emission delay between two states and also measured a delay. The funny thing was actually that the tunnel ionization, where you not only bring the electron out into the continuum, you actually have to spatially move it, and it's over many atomic units, actually was much faster than the single, it seems, the single ionization of a single photon. And of course the questions still remain, how does this scale between one photon absorption to 3 to 4 to n photon absorption, right? So these are all good questions which gets everybody excited, and some hardcore quantum mechanics physicists say any model is wrong anyway, but you know, I'm an experimentalist, I think models work really well, and the semi-classical models are actually extremely successful because then we become very creative and come up with a whole bunch of ideas. If you just do numerics, you lose your creativity. Sorry for the... I'm always open for discussions afterwards, right? For now, you have to listen to me. So, now, tunnel ionization. So the tunnel ionization, there have been papers going on. One of them is from Keldysh. And Keldysh also proposed the time in his paper from 1965. And basically, he predicted a so-called tunneling time for an electron to go through the tunnel barrier that was induced by the laser field. And for the intensity that we have been typically working at, you know, like 10 to the 14, 10 to the 15 watt per square centimeter in helium under 800 nanometer center wavelengths, the tunnel time he predicted would have been 200 to 400 attosecond. So this is rather slow, right? So for the attosecond domain, so we thought we can measure that. So how did we do it? It's the Attoclock. We called it the Attoclock. And basically what we used is a few cycle infrared pulse centered around 800 nanometer, which was circular polarized. So you all know when you have a circular polarized light, the electric field vector is rotating at the optical frequency around in a circle. So that means when you compare, when you look at the electric field as the hand of a clock, you actually have a time reference, right? Because the way we measure normally time with a watch, right? You have the hour hand, the minute hand, the second hand. So the faster it rotates, the more accurate is your time measurement. So now with this circular polarized light, we in principle have a hand of a clock that is rotating more or less in a femtosecond. And so we can easily have attosecond resolution. You know, you can easily measure 1 degree accuracy, fraction of degrees. So what do we measure with this electric field? We basically have a time reference that is something we can measure macroscopically, and is the same time and the same time reference. This is also acting microscopically on a single atom. So you have a defined time. And then what do you measure in addition? You measure basically also using the simplest way of using this Attoclock. You actually use this time reference also to induce the tunnel ionization. So, and then at the end you measure the electron that is coming out, and you measure the vector of the electron momentum, in what direction it comes out. Depending on the direction, it gives you the time delay of the tunneling. So I'll give you then, for the rest of the talk, more details, but let me then first give you the result. So we originally started off with helium, and you know, this one figure on the left shows you the helium data over a large intensity range, and basically the solid line would have been the angle of the electron coming out of the electron momentum, assuming it tunnels out with 0 delay, instantaneously. And you can see the angle is a little bit shifted, but you know, our arrow bars went actually through this 0. So actually we could put an upper limit on the tunneling delay, which was in the range of 35 attosecond. So far away from the 200 or 400 that Keldysh predicted. We then continue, you know, when you do measurements which don't agree with theory, you keep measuring, right? That's the best you can do. So we changed the target, went to argon, and argon we also did over a large intensity range, and you can see only in the lower intensity range the data was more above the solid line, which would have been instantaneous tunneling, and then otherwise it pretty much tracks the solid line. But when it took us a while to understand argon of the helium, because argon turned out to be much more messy. And I would like to explain that as well. And so at the end, to really resolve the tunneling delay time, we went actually back to helium. And these are the measurements that we did as an improvement. And now look at the quality of this measurement. So blue in the lower section is basically blue are the data, basically, which gives you the tunneling delay at this tunnel ionization process. The scale goes from 0 to 200 attosecond. And if you compare that to any other prediction of tunneling time, because tunneling time has been a heated, debated topic in theoretical physics with many different predictions. So above, you see a whole bunch of different predictions. For many of you know the names. You know, they're ranging from 800 to basically sub 100 attosecond predictions. So it's huge playground, right? And basically, you know, one of these tunneling times is from Pollock-Miller. Buttiker-Landauer is very similar to the Keldysh time. Then you have the Eisenbud-Wigner, then the Larmor, and you can see that our data is very similar to the Larmor tunneling time. And then the theoretician in my group, Dr. Alexandra Landsman, used the Feynman path integral formalism to actually explain our data with this triangular tunneling barrier, and basically could explain it with this one as well. And if you then look at what is the tunneling time as a function of barrier width, you can see on the lower, it's not arbitrary units, it's atomic units. So it's 8 to 20. So this is basically the electron going out pretty far away from the center of the atom. And you can see it pretty much follows more or less a straight line. And it's not, and it's slower than the speed of light. And it's much faster than just letting an electron propagate over the same distance with the kinetic energy of the binding energy, if you just right away would move away the barrier. So, I hope these are now our latest data that we still try to get published, actually. It's on arXiv. And I would like to explain to you a little bit in more detail how we measured it, because people really get very emotional about this kind of measurements. Where is the Heisenberg uncertainty principle? How can you do this? Let me answer these questions. Let me also emphasize, before I go on, we actually use the Attoclock technique also to resolve the timing in the double ionization. You know, where on the circular polarized light, you asked, you know, you can bring, if you increase the intensity, you can not only take one electron, you can take two out. Is there, are these two coming independently with circular polarized light? Or when is the second one coming in comparison to the first one? And there again, we basically showed that the second one comes much sooner than the first one, which was not predicted. And actually we showed some correlation, which was also not predicted. You know, when you looked at the ratio of the two electrons going in opposite direction versus into the same direction, if you circular polarized, you have no rescattering, which kicks out the electron. So you would predict equal distribution. We saw an oscillation. Was not predicted, and theoreticians are still trying to understand exactly what is going on under these things. So let me now go to the Attoclock and explain the tunnel ionization experiment. So we have this, I mean, generally people get have long discussions about time delays in quantum mechanics, because time is not an operator, and so you have to be very careful to define what are your observables, right? So what we are doing with the Attoclock, we do two independent measurements. One is the polarization of the light, and one is basically the electron momentum. And we all know the electron momentum I can measure with very high accuracy. I don't use any attosecond pulses here at this point. Of course, I can combine it. So just that you get used to it, I know not everybody here is an expert, so I use a short pulse, around 5 femtosecond. In the short pulse, the maximum of the electric field vector goes up in a circle, goes down again. So if you look at the magnitude of the electric field, it goes slowly up and then slowly down and rotates in the space. And when you look into the direction of the propagation, you have this hand of the clock going around. And because the tunnel ionization is such a highly nonlinear process, everything happens within around the maximum, because only there you have the necessary intensity to ionize, tunnel ionize the atom. So you take basically then this circular polarized light, and because you use this short pulse, it's actually very hard to do a perfect circular polarized light. Actually, you can't even do it. And you know, initially I thought that was a problem, but actually at the end it solved our problem with the time zero calibration. Because you don't want to have a perfect circularized polarized pulse. Because if you take a little bit of ellipticity, then the maximum of your electric field vector is given by the ellipticity, the main axis of your elliptical polarized light. So to say time zero is the moment where we have the maximum of the electric wave vector. This is time zero, because that initiates the tunnel ionization. It's the most probable trajectory, the most strongest signal. So this is actually the nice thing about the Attoclock. You have a well-defined starting point in the tunnel process of the most probable trajectory. So to measure the elliptical axis of a light pulse is very easy. It's just polarimetry. And it will not change when you go into the experiment. We actually have a sanity check. So this gives you time zero, and then the fast rotating electric field is then your time reference. So let me now show you. So you can go for a two-step model. The first step is you have a tunnel ionization, the electron goes out, and then keeps being accelerated by the electric field of the remaining part of the pulse. And so what I show you now is the rotating electric field vector at the maximum of the electric field. You have the tunnel ionization here. I assume it's 0 delay, and then the electron is treated semi-classically. You know, it's pretty far away from the core. You know from scattering theory that this works very well. We know from high harmonics that this semi-classical picture is very well describing high harmonics generation. So we treat then this electron afterwards in the remaining part of the laser pulse classically, and you can, in the simplest model, you assume Newton equation with the laser field alone. No other interaction for the time being. I'm coming back to that one. So I'll let this movie go. I hope it works. Yeah, electric field gets up, up, up. I look at the most probable point, maximum. Electron comes out instantaneously, keeps being accelerated by the remaining part of the electric field. And once the pulse is done, the electron comes out into a special direction with a certain momentum. And you can actually show mathematically very easily is if you just assume you're in the strong field approximation, you neglect the Coulomb interaction, actually the electron comes out exactly at 90 degrees removed from the maximum. So if there would be no tunneling delay, the electron would come out at 90 degrees C. But of course, there is also the Coulomb interaction, and that gives a little bit of a correction. And that was also a very heated debate. How do you include Coulomb correction into this dynamics? I'll address that as well. So basically, how do we measure the electron momentum? There is actually a very nice instrument that has been developed by nuclear physicists, the so-called coltrims. And that one measures the 3D electron momentum vector with very high accuracy. So let me show you that. So you have basically an instrument where in the middle you have a gas jet. There is your helium, then you come in here with your laser pulse. Normally you don't use a focusing lens, right? You take this all into account, but it's just to show. So you ionize, you know, every 1,000 pulse ionizes one atom. So it's really coincidence measurement. You then measure the ion and the electron simultaneously, and every event is a single event. You can measure basically on the both sides. You have a time of flight and the position detectors, which give you the vectors of the ion and the electron. So if you have only one ionization event, you can either measure the ions or you can measure the electrons to get the electron momentum. Now, in reality, we don't have only the laser field under the circular polarized light. So when the circular polarized light comes, ionizes the atom, you of course also have the electron-ion interaction, which in the helium is mainly the Coulomb potential. So you actually really have to add an additional term into your equation, which shifts a little bit the magnitude of your ion distribution. So you have here, this is your elliptical axis of your light. So the maximum is here, and under no Coulomb interaction, the electron will come out in 90 degrees C. That's where you have the highest count. Of course, you have a certain distribution, right, for the tunnel ionization. If you then take into account the Coulomb interaction, it shifts it a little bit, and it changes the direction. Would there be a delay, it would shift even more. So depending on the angle, you would actually be able to resolve a tunneling time. So, and as I say, the elliptical polarization gives me the time 0. So what you do is you use a quarter wave plate before you go into the coltrims apparatus to set your polarization. And before you go in, you can do also your full characterization of your polarization. So all you have to do, you insert after your quarter plate, before you go into the cold trims, a polarizer, and you characterize basically the polarization of your pulse. Depending on the angle of your quarter wave plate, you set the ellipticity and the axis of the main polarization. And the contrast gives you the ellipticity, and we normally work with an ellipticity of about 0.8. Not with 1, because 1 is undefined, and also with these broadband pulses, it's basically impossible to get perfect circular polarization. And then you need to get from this angle measurement, which is the time 0, a calibration between the laboratory frame angle and the electron angle measurement, right? You need a calibration. So how do you do this? So you basically ionize first the atom with a linear polarization where you don't have this angular streaking, and the direction of this linear polarization is where the electrons will go out, and you basically get a calibration between your polarization measurement and your cold trims measurement, and you set that one to 0. And then you go to the ellipticity and look at the angle offset from the maximum of your time 0, right? So it's a very straightforward way. And you can then take into account the Coulomb correction. Over time, we actually improved our signal to noise. These measurements are coincidence measurements. You measure ion and the electron at the same time. So it matters if you work with a 1 kilohertz laser versus 10 kilohertz laser. So I got the money to improve my laser after the original experiment. And this just shows you the quality of the data when you go from 1 kilohertz to 10 kilohertz, right? The peak search, because at the end, what you do is a peak search of your electron distributed, accumulated over many, many, many single measurements. And of course, this peak search becomes better. But you have another nice thing about the Attoclock, just to make sure that there is a sanity check. And this is, you can actually make the light go left and right circular. So you can actually change the orientation of your clock. And this is very nice, because you can easily show that this Coulomb correction will give you either a reduction to 90 degrees C or an addition to 90 degrees C. So you actually have a very sensitive measurement for this complex electron-ion interaction in this streaking process. And if everything is right and you're not making a mistake, you should actually measure both error for left and right circular polarized light. You should measure the same offset angle with regards to the 90-degree streaking angle, which would neglect this electron-ion interaction. And you can see that we get that, and what you can see below, this is the results that I showed you at the beginning with the improved laser system and extending the measurement to lower intensity, so that actually this tunnel ionization delay becomes a more measurable entity. You can see that if you increase the intensity, the error bars are kind of touching the 0 tunneling delay time, but it's clearly above. And as we lower the intensity, the barrier width becomes larger and larger, the tunneling delay is longer and lower, and you can see this offset is increasing, and blue and red are clock or anti-clock, which is a very nice way that we know that there is no systematic error in our angle measurement. And just to emphasize this more, all we are doing, so we have here, this is the cold trims apparatus, here is the gas focus, right? So we come in and focus into it. We have a window here, but for the polarization measurement, we insert here a polarizer and a power meter and do all this polarization, and then all it goes, when we then set the quarter wave plate, it goes through this window, and if this window would do some funny thing, we wouldn't get the offset plus minus 90 degree in the correct way, right? So this is done very accurately, and we understood the quarter wave plates, it makes sense, so we adjust the angle on the quarter wave and we switch between anti-clock and clockwise attoclock operation to measure those angles all the time. So it's a very simple and easy way. And so this offset angle to 90 degrees C turned out to be a very sensitive observable measurement to actually understand the complex dynamics of the electron moving away from the ion. Right? And so you can take into account the Coulomb and so on. And as it turned out, in argon, there is many more terms that you actually have to take into account. You can't stay in the single active electron approximation. You actually have to take into account the other electrons. And then think about when you remove an electron from a molecule, there is going to be dynamics on the attosecond time scale on the molecule, right? Here, as it turns out, we can treat the multi-electron effects of the argon like in a static. They are so fast that they are the same as in a static experiment. So how do we take into account the Coulomb interaction? Actually, at that time when I started, most people actually used a one-dimensional model to describe the ionization potential in the tunnel ionization, which is basically the Coulomb potential, right, and the electric field here for this bent Coulomb. So you have the Coulomb plus the electric field in one dimension. But this is actually not really the correct way, because you can actually go into the quantum mechanics textbook and you can show that you can actually solve the Schrödinger equation correctly if you go to the parabolic coordinates. If you go to the parabolic coordinates with the Coulomb potential, you actually get two potential, an effective potential in the eta coordinate here, which is slightly modified from the field, as we call it now, the field direction model, this one-dimensional model. It has some additional terms. It changes the exit point of the electron, and it changes the energy here. So it really goes into the semi-classical model, but this is the correct quantum mechanical solution for this problem. And if we take this into account, basically we can actually get the Coulomb correction very accurately done. In the argon, it's actually more complicated than that, because the Coulomb correction alone did not explain the result. So this figure tells you, this one shows you the tunnel exit point as a function of the field strength or intensity. And you can see that, the tunnel exit with increased electric field is going down. So the solid line is the field direction model, this one-dimensional model, and you would actually predict over barrier ionization much earlier. But if you actually use the parabolic coordinates, you correctly describe it, and you actually don't even reach the over barrier intensities over the electric field strengths that we have been working at. So when you look then at the angle of the electron coming out, assuming instantaneous tunneling, the field direction would actually give you then, of course, here a maximum at, when you reach over barrier, but over barrier in reality is never reached, and you can see it also in the data. This is continuously decreasing. And the Coulomb correction gives you this line. And the Coulomb correction wasn't really enough. So we had to, was the contribution from Lars Machen's group, we had to take into account in argon that you actually have a Stark shift, which is under the electric field, which is well known and has been described before. So we took those data. Again, a correction, but then you also have an induced dipole, which is well known in argon, with the leftover electrons. They rearrange, and if we take this into account, we get the agreement, and no measurable tunneling delay time at these really high intensities. Look at the Keldysh parameter here. And only at the lower intensity we see something like going up. But it was clear to us, okay, if we really want to concentrate on the tunneling delay, we really need to go back to helium and just do the measurement more accurately, and that's what we did. by going to 10 kilohertz pulse repetition rate and going to lower intensity. Now, when you go to lower intensity, the probability of the ionization is becoming lower and lower. The count rate on the coltrims becomes, even at 10 kilohertz, negligibly small. I mean, you end up into noise. And so we actually expanded the measurement by going to a VMIS. And what you are seeing here is an overlap. So we made sure that on the overlapping part, the data, the solid data points here are the VMIS data, which are overlapping. Here is the coltrims data. And these are the coltrims data, which we couldn't expand to lower intensity because we simply didn't get enough counts anymore. So the VMIS is a velocity imaging of also the electron momentum. It's basically through an Abel projection going up into the to the detector. It's a little bit, don't have time to explain this in more details, has been described here extensively in this reference. But you lose a little bit of information because you make a projection. So you need to have some tomographic reconstruction to ultimately get the 3D distribution, but you can do that because instead of turning the whole apparatus, all we did is just turning the elliptical axis, right? In space, which we did with an additional half-wave plate, and made sure, that we rotated the incoming elliptically polarized light before we go in and measure all these different projections. And out of all these different projections, we ultimately can go through the tomographic reconstruction, the 3D distribution, and therefore the maximum direction of the electron. And this shows you, for example, the top graph shows you integrate the counts. You radially integrate the counts of the electrons, and you clearly can see in what direction you have the maximum of the electron counts, which is the most probable electron trajectory. And it's the peak search that you use for the delay. So with this, we were able to get this angle offset with regards to the 90° C. And then, of course, we want to get out of this angle, we want to get the tunneling delay, right? How do we do this? So we have the frequency omega tau is basically the offset angle from 90° C, because the 90°. Then we have basically the two corrections. One is the streaking, which I explained to you, which is the Coulomb correction for helium, which is very well described theoretically. So we can do that one. And then there is an additional correction that has been discussed in the literature extensively. And this is the correction assuming, is this adiabatic approximation that the electron comes out with zero velocity at the exit of the tunnel, or does it have some other, the most probable trajectory, does it have some other velocity? There's a whole bunch of theoretical predictions, so where is the starting point for this electron? What is the initial velocity? And when we take into account all the theory that has been published so far, over here, we can get only a small correction. So this would be a lecture on its own to explain to you all the different corrections. But basically down here, I'm now into the graph. I show you what would be the angle, assuming zero tunneling delay, where would be the offset angle with all the different corrections that have been predicted so far, taking into account all possible theories. So basically that would be one, another one, another one, another one. And as you can see, only small correction, the offset is still there, right? So if I take this into account, then for the tunneling delay time, putting it all in and putting, for example, the red curve gives me this data, then the black one, which is on the other side of all the theoretical prediction, gives you that tunneling delay time. right? And if and of course, if I have a finite tunneling delay time, then the electron doesn't come out at the maximum of the electric field, but actually a little bit later. So I need to take this into account in the streaking, gives also a small correction, but you can see it's all within the error bar, and it doesn't really change the message. We have an offset. So, is this offset now tunneling? If you have a different suggestion, come to me. Let's talk about it. We actually have a young theoretician in my group, and she used the Feynman path formalism, which has been developed over the years to actually explain all the different predictions of tunneling time. And if she applies it to the triangular potential, she can actually explain our data. So the solid line is the theoretical prediction for the tunneling delay time using Feynman path integral formalism. And the Feynman path formalism has the advantage that that one is well defined. It's a kind of a deterministic trajectory. So each path, you can clearly define a time during which an electron is within the barrier and define that one as the tunneling time. And as I showed you before, I mean, this tunneling time is is definitely slower than the speed of light. It's not instantaneous, and it's faster than the Buttiker-Landauer, the Keldysh time, and the time it would take if you would just leave the electron propagate with the kinetic energy over the same distance, which would be the upper limit. And so I hope with this I could give you a pretty clear description how we measured this attosecond process, defined to you the observables that we had. We measured momentum, and the time bandwidth product is the location of the atom that has been ionized, which is a macroscopic focus of the laser. So that is I can measure momentum with as much accuracy as I want, fraction of a degree, which means attosecond time resolution. But the interesting thing, if the theory is correct with the Feynman path integral, that theory would also predict that actually there is a fundamental uncertainty how fast the hole can be created. So it is a statistical process, and you would have so you cannot say the instant when the electron was ionized. You would have an uncertainty of the hole dynamics, which can be significant and would have to be taken into account. It's a very asymmetric delay, which goes into the range of 100 attosecond, which would give you a very fundamental uncertainty when you want to look at the dynamics of pulling an electron out and see how the holes are rearranging in the solid or in the molecule. And with this, I would like to conclude, and thank you very much for your attention.
Thank you very much, Professor Keller, for this exciting and intriguing talk.